I'm Talis. The project is Cancer Detection with Deep Learning. The outline of this video covers introduction, data processing, models and experiments, results and analysis, and conclusion. Introduction. We first want to answer the question, what is the project about? The project aims to build a deep learning-based system that automatically detects cancer region in pathology images. An example will be the following. So on the left-hand side, we have an input image, and the goal is to predict something similar to the one on the right. The yellow region is the detected cancer regions. Why do we want to do this? A deep learning system is likely to be a lot more scalable than any human beings. And also, given the amount of training data that a model can use, it's likely to be more accurate. Having such an assistive diagnosis tool is going to help us lower the risk of misdiagnosis as well. The objective of this project is to build a proof-of-concept prototype. We will also experiment multi-scale ensemble models based on the idea proposed in this paper. And we want to design appropriate evaluation metrics to evaluate and analyze our results. In our implementation, we build models on slide level 5 and slide level 7, and we generate a heat map on slide level 7. The models for different levels are trained independently. The second part is data processing. As the images are super large in size, we extract patches from them to feed into our deep learning network. So the patches of size 299 by 299 are extracted from the slides which we stored on Google Cloud Storage. We define a region of interest for every patch extracted. The region of interest sits in the center of the patch. And we sum the pixels within the region of interest on a mask and use this to determine the target class. For training and validation set, we're using 6 slides. And for training and validation set, we randomly extract patches. We also do undersampling on the majority class to ensure the class are balanced. For the test set, instead of randomly extracting, we use sliding window across the entire slide. And we use a slide that is completely unseen in our training and validation set so that there is no overlap in the slide information. We also maintain the class ratio as it is. Let's first take a look at the data to see what we're dealing with. Displaying a slide at level 5, which looks like this. We display the mask at exactly the same level, so it looks like this. The yellow region is the region of cancer. We overlay the two, and we want to be able to produce a mask like this, which we can know exactly where the cancer is. One important trick that we use in extracting the pixels is that we would like to ignore non-tissue area. Many of these gray pixels are not corresponding to any tissue region at all. And in areas that there is no tissue, it's impossible that there is cancer. So we can basically ignore this area in extracting the patches. We define the find tissue pixels function, which takes an image and check which pixels in this image are tissue by excluding the pixels that are too low in intensity. This picture, where the red ones are the tissue pixels. So we only extract patches out of these tissue pixels. For every part else, there is certainly no cancer, so we don't bother making a prediction on that or training on that. So we're doing training and validation set on these 6 slides. This part demonstrates the one for level 5, and there's also a similar one for level 7. The size of the grid is 299 by 299, and for every slide we extract 120 samples, 60 per class. So the first thing we do is that we compute the tissue pixels for this particular slide. And out of those tissue pixels, we will randomly select one, and then read the image grid, the mask grid corresponding to the pixel. So we have a patch where the center is this particular pixel. And then we will determine the sample class, whether it's positive or negative. So we first define the region of interest in this particular patch, which is the center pixels. So as we're outputting a heat map on level 7, and we're extracting patches now from level 5, so there is a scale of 4, which is that a single pixel in level 7 corresponds to 4 pixels in level 5. So our region of interest on level 5 will then be the center of 4 pixels. So it tracks these 4 pixels, and we check whether the sum is positive or 0. If it's positive, then we know it's a positive sample, so it's a cancer, and else it's negative. We have a 8-to-2 train validation split here, and this is how one patch would look like. We extract the test data on slide 110. So we no longer do random sampling. Rather, we do sliding windows. So just 2 for loops, and we slide a window. Similar method of extractions and computing the class. These are identical, except we do sliding window instead of randomly selecting. The transfer learning convolutional network base we choose is VGG16. This choice is based on the results, because we found that the results of VGG16 is better than the results of Inception v3 or MobileNets, which are other models that we tried. The features extracted from the VGG16 model is then fed to a neural network, which is just a single dense layer with 512 units, rel activation, and RMS-prop optimizer. The reason we're choosing RMS-prop instead of maybe Adam, the default choice, is because, well, the first reason is empirically some suggest that Adam sometimes produce worse result on the test set than RMS-prop. Well, empirically that happens as well in our case. And secondly is because there is arguably some mistake in the proof of the Adam optimizer, although it still works pretty well in many cases, but it still seems like a black box to me. And I think using RMS-prop is better because the flow is better understood, at least for me, and it will be therefore easier to analyze and also more feasible to diagnose problems from my point of view. So that's why we're choosing RMS-prop. After that, we have a dropout layer. That's the neural network part. Alternatively, we'll also test in our model, which is random forest. So after the features are extracted from VG16, we also fed it into a random forest model, which has 200 estimators with maximum tree depth 8. These two are based on the grid search results we obtained, the best model, the smallest best model. So the model of transfer learning together with dense layer looks like this. So in our experiments, we have essentially 4 models. For level 5, we have 2 models. One is transfer learning with dense layer. The second one is transfer learning with random forest. So this is the model for level 5. We have a very similar one for level 7. So we have separate directories for training, validation, and test data. And we first load the VGG model using ImageNet weights. This is our transfer learning part. This is how the model looks like. And we take this extracted feature as input to train our dense layer. Before that, we have to extract training features, extract validation features, and extract test features. Now here's our dense layer model. So we have dense layer, dropout, and then a softmax layer. Note that we're using RMS-prop here, as we described earlier. Now we fit the model, and we obtain the model. So we save the model, and make sure that we are able to load it back from the file we saved. Similarly, we build a random forest model, trained also on those training validation features. So here we have a number of estimators maxed out as described, and we also similarly store this model for results. Now we have the models. We have to think about how should we evaluate the models. We evaluate the model both quantitatively and qualitatively. For a quantitative evaluation, we use some metrics. The first metrics, most naively, is the accuracy. But accuracy is not a very good metric on our dataset because our test set is highly imbalanced. So we then consider precision recall and F1 score. We had to understand the meaning of these to determine whether they're suitable for our case. So looking at precision heavily means that we want a model with low false positive. False positive in our case means that we have a prediction of positive, whereas it's actually false. So it's actually negative, but we're predicting positive. That means there's actually no cancer, but we're saying cancer. So this is perhaps not as serious as the other way around, which is recall. So recall cares more about having low false negative. That means we're saying negative, but it's false. So we're saying negative, but it's actually positive. We're saying no cancer when there's actually cancer. Now this is very serious because if there's cancer and saying no cancer, that means we're missing the opportunity to treat this patient properly. So that will be a serious misdiagnosis. Whereas for false positive, we just pass it on to maybe a second screening and so on, if the result is not as serious. So I think in our case, we will care more about recall rather than precision. And we also use area under ROC curve as a metric because it's generally a good metric for imbalanced data. And lastly, one more thing we look at is the average confidence level of the model on erroneous prediction. So this means we take out the erroneous prediction samples and average the confidence levels on which our model makes the prediction. So that means like we want to know how confident our model is when they did something wrong. Essentially, if a model has a very high confidence level when making a mistake, that indicates somewhat bad a model. On the other hand, if the model is actually very, very uncertain, very, very unconfident when making an erroneous prediction, that is a better model than the previous case. So we look at the average confidence on erroneous prediction as one metric as well. On the qualitative evaluation aspect, we inspect manually the test samples that causes these erroneous predictions. And we also look at the quality of the heat map produced by the model. So we take a look at the error causing samples. We know that our test data is pretty imbalanced. Right, so here are the 3 samples that our model makes a mistake on together with the confidence level. So here we make a false positive with a pretty low confidence. Here we have a false negative with pretty high confidence. Well, this is a little bad. And here another false negative, which with also a pretty low confidence. So the average mistake confidence here is 0.72. I think this is actually not very bad. It's actually quite okay. And we also look at the precision recall F1 score here. So we got a positive clause being 1. So here, the recall is 0.82 is okay-ish. It's not very good, and the precision is quite good. Right. We also have the others, macro, and weight average. The area on the curve here we have 0.98. Wow, that's pretty good because the ideal case is 1, and this is pretty close. Let's look at a patch for which we want to generate a heat map on. So here's the patch, and this is the corresponding mask. That's the result when we overlay the two. And here we ensemble our models. We load the predictions from all the models, and we do a weighted average here, and we produce the heat maps. So these are the heat maps, and the bottom ones are the mask corresponding to the heat maps. Let's take a look at these versus the ideal case, the ground truth mask. First observation is that level 7 models does not seem to perform very well in this case, and although the prediction seems to make sense, but they're not quite good. Whereas for level 5 models, the prediction is a lot better with this ones. And one interesting thing is that we see that for the neural network models, these areas are predicted with a very, very low probability of cancer. So that is these areas. So it's kind of missing something here, right, where there's actually something. And for the random forest model, on the other hand, it gives actually higher probability for these areas. I think the ensemble of these two is certainly helpful because it's able to capture more of these on certain regions. This image patch is probably hard, as we see like there is some non-cancer region within cancer region or between. So it's not as simple as just an entire block being cancer. So it's a little hard. And in our case, we're seeing how that reflects as uncertain probability. So an ensemble in this case will help. And the ensemble heat map is perhaps closer to what we would like to see. But an ensemble with these two is perhaps not helpful because these predictions are only making things worse, given that there's actually no cancer here. Part 5 is a quick summary and conclusion. So in conclusion, we have built a proof of concept prototype, and we see that multi-scale ensemble, in this case, is not helpful. It's not helpful to use both level 5 and level 7 for a heat map prediction on level 7, because level 5 alone does better. And an ensemble of different model types is helpful in our experiments that averaging the results of random forest and a dense layer is better than either one alone. Thank you for watching.